Welcome to the study of the Fourier Transform. I often call this the major secret of the universe. Why? Because it reveals that everything we perceive, light, sound, even data, is made of hidden ingredients called frequencies. We are going to walk through the principles laid out by Professor Brad Osgood. We aren't just looking at math, we're looking at a different way to perceive reality itself. We begin with Chapter 1, the periodic world. Nature loves cycles, and historically, we started by analyzing things that repeat. A function is periodic if it repeats its values at regular intervals. We define this as f of t plus t equals f of t, where t is the period. Think of a clock. Whether you look now or 12 hours from now, the hands are in the same place. This is the essence of t. But what happens if we stretch the time between repeats to infinity? The repeats disappear, and we transition from a Fourier series to a Fourier transform. Every signal has a spectrum. You can view a signal in the time domain, watching it happen, or the frequency domain, seeing what it's made of. To build these signals, we use sines and cosines. But to make the calculus easier, we use complex exponentials. This formula sifts the signal. The integral calculates how much of frequency n is present in f of t. There is a vital theme of reciprocity. If the period in time is large, the spacing in the spectrum is small. They are inversely related. A famous warning, the square wave. If you try to build sharp corners using smooth sines, you get ringing at the edges. This is the Gibbs phenomenon. As Osgood says, it takes high frequencies to make sharp corners. Think of drawing with a fine-tipped pen versus a thick, blurry crayon. Geometrically, we treat functions like vectors. We can project a signal onto a frequency using the inner product. This leads to Rayleigh's identity. The energy in the time domain equals the energy in the frequency domain. Energy is preserved. Fourier actually invented this to solve the heat equation. Consider the cellar phenomenon. Deep underground, seasonal temperature changes are damped and shifted. It's cool in summer and warm in winter, because the wave of heat takes 6 months to travel down there. Chapter 2, the Fourier Transform. When we move to non-periodic signals, we transition from the rect function, a simple switch, to the sinc function. Now, we don't have a discrete list of frequencies, we have a continuum. The integral now spans from negative infinity to infinity. Consider the shift theorem. If you shift a signal in time, the energy stays the same, but the frequencies undergo a phase wrap. Then there is the stretch theorem. Squeeze a signal in time, and its spectrum spreads out in frequency, like an accordion making a higher, wider sound. And the miracle, the Fourier transform of a Gaussian bell curve is another Gaussian. It is the perfect shape that looks the same in both domains. Chapter 3, Convolution. This is one signal modifying another. In the time domain, it's a complex sliding integral. But in the frequency domain, convolution is simply multiplication. This is how we filter noise or blur images. The central limit theorem shows nature's preference for smoothness. Convolve any shape with itself enough times, and it becomes a Gaussian. Finally, we have the Dirac delta, the impulse. It's infinitely thin and infinitely tall, yet has an area of exactly 1. String these spikes together, and you get the Shaw function or Dirac comb. This is how we sample digital audio. If you don't sample fast enough, high frequencies pretend to be low ones. This is aliasing, like wagon wheels appearing to spin backward in old movies. The Fourier transform isn't just a formula, it's the lens through which we view the universe. From MRI scans to your cell phone, it's the math that powers the modern world. If you found this journey through the frequency domain helpful, please like and subscribe.